Buenos días, autoridades, queridas vocales de la Comisión de Mujeres y Ciencia, de la presente, de las pasadas, de la protocomisión, futuras investigadoras e investigadores, compañeras y compañeros presentes y en remoto. Soy Pilar López Sancho, del Instituto de Ciencia de Materiales del CSIC, y en nombre del CSIC y de la Comisión de Mujeres y Ciencia les voy a acompañar en este acto en el que celebramos dos importantes acontecimientos: la entrega de la medalla de oro del CSIC a la profesora Strickland, concedida a propuesta de la Comisión de Mujeres y Ciencia en junio de 2020, y los 20 años de funcionamiento de la Comisión de Mujeres y Ciencia, que se cumplieron en septiembre de 2022. Diferentes circunstancias han retrasado la celebración de estos acontecimientos, que ha sido posible gracias al apoyo de la presidenta del CSIC, de la vicepresidenta ejecutiva de la Comisión de Mujeres y Ciencia y del gran trabajo del Gabinete de la Presidencia y de su Departamento de Protocolo. Les va a dar la bienvenida la presidenta del CSIC.
Querida ministra de Ciencia e Innovación, Diana Morán, embajadora de Canadá, Wendy Ducrier, profesora Strickland, galardonada con la medalla de oro del CSIC, queridos presidentes del CSIC y presidenta, que sé que algunos no están aquí, pero nos están viendo en remoto, querida Comisión de Mujeres y Ciencia del CSIC, que tengo el honor de presidir, querida Carmen, que sé que no estás hoy aquí con nosotros, pero también nos ves en remoto, Carmen Mayoral, querida Teresa, que no sé dónde está, querida Teresa Valdés Solís, que es la vocal de la Comisión Mujeres y Ciencia y que hoy estará aquí con nosotros, querida Pilar López Sancho, que es vicepresidenta ejecutiva de la Comisión de Mujeres y Ciencia, queridos amigos y amigas, queridos a los que están aquí y también a los que nos siguen por streaming, queridos estudiantes, a las y los estudiantes que están hoy con nosotros y que nos hace una alegría, que nos da una alegría especial que estéis aquí hoy. Es un honor darles la bienvenida al Consejo Superior de Investigaciones Científicas y agradecerles que nos acompañen en un día tan importante y tan relevante como este para nuestra institución. Es un día de celebración, de fiesta, de alegría, porque concedemos el mayor honor de la institución a la profesora Donna Strickland y, sobre todo, y más importante todavía, tenemos el honor de que la profesora Donna Strickland, Premio Nobel en Física en 2018, lo haya aceptado la medalla de oro del CSIC y esté hoy con nosotros en esta celebración. Como muchos de ustedes saben, el CSIC es una de las instituciones de ciencia e investigación más importantes de nuestro país y una de las más importantes de Europa. Formamos parte del G6 de la ciencia. Somos cerca de 14.000 personas que trabajamos por la ciencia en todo el territorio nacional, pero más importante que estas cifras del CSIC es lo que el CSIC hace. Somos una institución de ciencia fundamental. Y tenemos como misión contribuir al avance del conocimiento. Aspiramos, junto con otros científicos y científicas del mundo, a conocer mejor el mundo, a explicar mejor el mundo desde todas las áreas de la ciencia, desde las ciencias sociales, desde las humanidades, las ciencias de la vida y las ciencias de la materia. La profesora Strickland es una firme defensora de la ciencia fundamental, de la ciencia básica, como decimos normalmente en España. Ella en varias entrevistas ha explicado que cuando estaba investigando en CPA, ella no estaba buscando la cura para enfermedades oculares, estaba tratando de ver si un átomo podría absorber más o menos fotones. Y luego, efectivamente, estos descubrimientos cambiaron las normas de cómo interacciona la luz con la materia y esto ha tenido, después de muchos años, muchas aplicaciones de las que hoy todos nos beneficiamos. El CSIC es, por tanto, una institución de ciencia básica y estamos muy orgullosos de ello, pero también tenemos tenemos un fuerte y un creciente compromiso con el desarrollo económico, social y cultural de nuestro país y con el progreso de la humanidad y de los otros seres vivientes, como diría Peter Singer, el filósofo Peter Singer. Por eso estamos haciendo también un fuerte esfuerzo estos años en la transferencia del conocimiento. Esta misma semana, el Gobierno de España y en concreto el Ministerio de Ciencia e Innovación ha reconocido este esfuerzo. 8 de los 20 premios nacionales de investigación, el máximo reconocimiento en nuestro país, han ido a parar a científicos y a científicas del CSIC. Y es raro, les tengo que decir, la semana en la que no tengo que levantar varias veces el teléfono para dar la enhorabuena y felicitar a colegas, a científicos y a científicas del CSIC que han recibido un reconocimiento internacional o han realizado algún hallazgo científico muy importante. Es verdad que el Nobel se nos resiste, pero estoy segura de que pronto podemos anunciar. Una de esas mujeres reconocidas está hoy con nosotras y va a hacer la laudatio de la profesora Strickland, es la profesora Pilar López Sancho, que aunque ella es muy modesta y seguro que no le gusta nada lo que estoy diciendo, tiene el premio de Minuta de la Sociedad Europea de Físicas. El CSIC hoy es una institución vibrante, es una institución moderna que está haciendo una apuesta muy importante por abrir nuevas líneas de investigación. Con el apoyo del Gobierno de España, además, hemos logrado renovar nuestra apuesta por la tecnología de última generación, tan importante para hacer ciencia, por ejemplo, en el ámbito de la inteligencia artificial. Nos estamos esforzando mucho por atraer y retener el talento internacional y también por apoyar a los investigadores, y aquí miro al fondo, a investigadores y a investigadores jóvenes. Hoy algunos están todavía en el instituto, pero esperemos que dentro de unos años estén en el CSIC. Y por, como les decía antes, nos esforzamos también en la innovación y en la transferencia del conocimiento, en devolver a la sociedad española todo lo que la sociedad nos da. También somos una institución que sabe que lo que los científicos construimos, lo construimos a hombros de gigantes. Déjenme que utilice esta frase que no es nada original, muchos de ustedes la conocen bien, pero es una frase muy oportuna hoy, porque es una frase que se le atribuye a Isaac Newton en una carta que escribía a sus colegas y en la que reconocía que él había llegado a conclusiones sobre las propiedades de la luz gracias al trabajo pionero de Descartes o Hooke, por ejemplo. Hoy la medalla de oro del CSIC se la otorgamos, se la concedemos a una investigadora de la luz, precisamente, a una investigadora que ha trabajado en las herramientas hechas de luz. La medalla del CSIC, la medalla de oro del CSIC, es un reconocimiento singular. Hemos reconocido desde 1987, que es cuando la pusimos en marcha, hemos otorgado 20 medallas de oro del CSIC y se las otorgamos a personas o a instituciones que iluminan el camino de la ciencia. La NASA tiene la medalla de oro del CSIC, también algunos responsables públicos, algunos expresidentes del Gobierno que han apostado por la ciencia, pero sobre todo se la hemos otorgado a científicos y a científicas. Muchos de ellos, no todos, como por ejemplo Stephen Hawking, muchos otros. Él no tiene el Premio Nobel, como saben, pero sí otros que han tenido el Premio Nobel. Sobre todo hemos premiado a premios Nobel en medicina, en física o en química. En estos años hemos premiado a 3 mujeres que han sido también premios Nobel en medicina y 2 en física, una de ellas la profesora Donna Strickland, por su investigación en el desarrollo de láseres ultracortos de alta intensidad, por el que, como les he dicho, recibió el Premio Nobel de Física. En este caso, saben que la profesora Strickland fue la 3ª mujer en recibir el Premio Nobel de Física, ahora ya tenemos 4, pero también sabemos que de los 222 premios Nobel en física que existen entre 1901 y 2022, solo hay 4 mujeres. Son muy pocas. El CSIC es muy sensible a esta infrarrepresentación de las mujeres, que nosotros también sufrimos en nuestra institución y por la que estamos trabajando mucho, en particular gracias al impulso de la Comisión de Mujeres y Ciencia, que hoy cumple su 20 aniversario y a la que me gustaría que todos honrásemos ahora con un aplauso. Queridas colegas, queridas compañeras del pasado, del presente y del futuro de la institución, muchas gracias por toda la labor que estáis haciendo. Aún así, como luego nos contará Teresa, estamos todavía lejos de nuestros propósitos, queridas, y necesitamos el apoyo de todas, también de nuestros compañeros. Sin vosotros será muy difícil conseguir todo lo que aspiramos. Quería agradecer a la Comisión justamente la propuesta de conceder a la profesora Strickland la medalla de oro, porque necesitamos visibilizar a las mujeres, necesitamos científicos y científicas, necesitamos a todos los que estáis por ahí detrás. Esta es una profesión noble y maravillosa y os necesitamos a todos, pero queremos también decirles a las chicas que este es un sitio donde se puede llegar y que pronto pueden estar en nuestros laboratorios usando nuestros microscopios y nuestros telescopios para hacer ciencia. Os esperamos. Todos necesitamos musas y ya sabéis que la palabra musas, que hoy sería lo de influencer seguramente, musas se usa en femenino y en masculino. Esperamos que la profesora Strickland sea nuestra musa, la musa de todos los que estamos haciendo ciencia y la musa de todos los que están por venir. Por favor, únanse conmigo también a dar la bienvenida a la familia de la ciencia española y la familia del CSIC a la profesora Donna Strickland.
Muchas gracias, presidenta. Ahora, Teresa Valdés Solís, vocal de la Comisión Mujeres y Ciencia, en nombre de la vicepresidenta ejecutiva de la Comisión, Carmen Mayoral, nos va a hablar sobre el trabajo de la Comisión durante estos 20 años y la importancia que ha tenido para el CSIC.
Buenos días, señora ministra, señora embajadora de Canadá, presidenta del CSIC, profesora Strickland, autoridades, asistentes, muchas gracias por compartir con nosotros este 20º aniversario de la Comisión Mujer y Ciencia. Quienes formamos parte de ella estamos además muy agradecidos de la oportunidad de hacerlo en el marco del acto institucional más importante del CSIC, como es la entrega de nuestra medalla de oro. El principio de este siglo vino marcado por una profunda preocupación en Europa acerca de la infrarrepresentación de las mujeres en la ciencia y en la academia, sustentado en estudios formales y en datos como los recogidos en el informe ETAN de 2001, que indicaba que la infrarrepresentación de las mujeres amenaza los objetivos científicos de alcanzar la excelencia, además de ser un derroche y una injusticia. En España, la reivindicación afloró en 2001, en el acto de celebración del Día Internacional de las Mujeres, en este mismo lugar. Aquí y entonces se llevó a cabo un seminario y un activo debate donde nuestras compañeras pusieron de manifiesto la necesidad de estudiar la situación real y concreta de las investigadoras del CSIC. El entonces presidente del CSIC, Rolf Tarrach, tomó en ese momento conciencia de esta necesidad y estableció un grupo de trabajo para hacer lo que mejor sabemos hacer en ciencia: estudiar los datos y presentar un estudio con los mejores datos posibles para analizar esa participación de las mujeres en el CSIC. Esos trabajos darían lugar a los primeros informes de mujeres investigadoras y constituirían el germen de lo que hoy es la Comisión Mujer y Ciencia. La implicación de las investigadoras del CSIC fue muy intensa. Más de 70 personas participaron en la elaboración de un monográfico sobre el CSIC publicado en la revista Arbor en el año 2002, donde se analizaba en profundidad la situación de las investigadoras en todas y cada una de las áreas del CSIC con las características propias de cada una de ellas. Muchas de estas mujeres, auténticas impulsoras de la igualdad en nuestra institución, nos acompañan hoy en esta sala y queremos aprovechar para agradeceros vuestro compromiso, vuestro impulso, vuestra convicción y todo el trabajo que habéis realizado y seguís realizando y el apoyo que nos habéis brindado a la Comisión Mujer y Ciencia del CSIC. El Consejo respondió a este impulso y a las recomendaciones europeas para proporcionar datos fiables y accesibles sobre la situación de las mujeres en la academia, creando oficialmente la Comisión Mujer y Ciencia el 30 de septiembre de 2002, a propuesta del presidente Tarrach y con el informe favorable del Comité Científico Asesor. En 2002 no existía en España ningún otro organismo que tuviese una estructura semejante en cuestiones de igualdad, y el CSIC se adelantaba en varios años a las primeras disposiciones legales al respecto. La tarea de la Comisión Mujer y Ciencia era y sigue siendo en la actualidad asesorar a la presidencia de CSIC en el estudio, seguimiento y optimización de la carrera científica de las mujeres en el CSIC. Nuestra misión es, en definitiva, alcanzar la igualdad de género y de investigación en el CSIC. Los primeros 10 años pasaron rápidos y llenos de trabajo. Partíamos de una situación en la que las mujeres eran solo un 31% del personal investigador en plantilla. Desde el principio se puso énfasis en los datos, se analizaron por áreas, por grupos, por escala y también se realizaron proyectos específicos, como los informes especiales sobre la composición de tribunales de evaluación, en los que de nuevo el CSIC tomó la iniciativa frente a otras instituciones, obligando por norma una composición paritaria de los tribunales a la vez que avanzaban las leyes nacionales al respecto. Se formó parte de acciones horizontales, se participó como expertas en encuentros, seminarios y foros, liderando la transformación cultural de género de la institución. Y tanto el CSIC como la propia Comisión empezaron a ser reconocidos como instituciones de referencia sobre cuestiones de género, mientras que las mujeres del CSIC ganaron prestigio y visibilidad gracias a su excelencia científica y al trabajo interno de la Comisión. Pero la Comisión, tras esos 10 años, era inequívoca. Pese al posicionamiento de la Comisión y su prestigio, alcanzar la igualdad estaba resultando lento, la aplicación de medidas resultaba limitada y era necesario desarrollar esa transformación cultural en una realidad estructural que, por supuesto, debía ir acompañada de cambio de políticas y de compromiso institucional. Por ello, a las funciones inicialmente definidas, como era elaborar los informes anuales de datos y el seguimiento de los resultados de plazas del personal científico, se incorporaron de forma natural nuevas funciones. La Comisión Mujer y Ciencia participa entonces en la creación de la Comisión Delegada de Igualdad y, junto con ella, en la elaboración y evaluación de los sucesivos planes de igualdad, así como en el desarrollo de los principales proyectos de igualdad del CSIC, como son el distintivo de igualdad y el desarrollo de los protocolos de acoso, de nuevo, de forma pionera en España. Así, el CSIC tiene una doble estructura de igualdad que continúa vigente, que trabaja de forma sinérgica para toda la institución. Se moderniza la Comisión, ampliando de forma natural sus funciones hacia la sociedad, la educación, la divulgación y contribuyendo sin duda a la visibilidad del trabajo de las mujeres investigadoras como expertas en medios de comunicación, en foros especializados, en estructuras internacionales y en puestos de representación y gestión. En este segundo periodo, la Comisión toma el papel de representación de la institución en cuestiones de género y se comienza a participar en redes nacionales e internacionales de género en investigación, con colaboraciones directas, pertenencia a grupos de trabajo y actividades de formación, entre otras. Toda esta actividad se refleja en los documentos de memorias anuales que se publican en la web de la Comisión, junto con otros documentos específicos y en la participación en muchas actividades conjuntas con un gran número de instituciones, tanto nacionales como internacionales. Nos gustaría resaltar que en el año 2020 la Comisión de Mujeres y Ciencias del CSIC obtuvo el reconocimiento de Science Europe como ejemplo de buenas prácticas al considerar que la existencia de una comisión específica para el estudio de las causas de la dificultad de acceso y progreso de las mujeres, con capacidad para proponer medidas de mejora, era un modelo a seguir en las instituciones europeas. Si hay un documento, un trabajo que está intrínsecamente relacionado con la Comisión, es el informe Mujeres Investigadoras. En el volumen que tienen en sus manos se recogen los datos correspondientes al año 2022 y se presenta un anexo en el que se muestra la evolución temporal de algunos de los indicadores que estudiamos. Este informe, su elaboración, análisis y difusión, que es la verdadera carta de presentación de la Comisión, no sería posible sin el compromiso firme y la cooperación de muchas personas pertenecientes a todas y cada una de las unidades y vicepresidencias a las que solicitamos los datos, que han entendido que en el dato está el conocimiento de la institución y que la perspectiva de género contribuye a la excelencia científica. A todas ellas queremos reiterar de nuevo nuestro agradecimiento más sincero. Y si intentamos condensar 20 años en una única gráfica, tal vez la más representativa sea la que ven en la imagen, la que muestra la evolución del índice de techo de cristal desde 2001 hasta la actualidad. Este índice, el valor 1, indica una situación de igualdad de oportunidades de acceso y promoción, mientras que los valores que superan la unidad indican la existencia de un techo de cristal. Hace 20 años, el CSIC acometió un proceso de modernización y mejora que nos llevó en la década de 2010 a valores de igualdad mejores que las de las instituciones semejantes en el entorno nacional e internacional. Sin embargo, los últimos años muestran un retroceso en esta tendencia que es ciertamente preocupante. Aunque es nuestra obligación poner sobre la mesa hoy, en un día de celebración, las cuestiones que permanecen sin resolver, también queremos poner de manifiesto que continuamos trabajando para conseguir un CSIC más igualitario y mejor, y que entre los proyectos que tenemos en marcha se incluyen análisis sobre la situación en campos concretos del conocimiento, el desarrollo de argumentarios basados en estudios de caso de acciones positivas internacionales y regionales o la creación de guías de trabajo para la incorporación del género en los contenidos de la investigación que entendemos que nos llevarán a un CSIC más excelente. Pero, sin duda, lo más gratificante de nuestra tarea es el reconocimiento de la excelencia de nuestras compañeras. Las investigadoras del CSIC, igual que los investigadores, aspiramos a la excelencia y los datos, siempre los datos, indican que nuestras compañeras, como comentaba la presidenta, están recibiendo numerosos reconocimientos. Por nuestra parte, intentamos contribuir a vuestro éxito presentando y apoyando vuestras candidaturas a los premios más prestigiosos, así como intentando cambiar las cifras y proponiendo reconocimientos como este que nos reúne hoy para otorgarle la medalla de oro del CSIC a la profesora Strickland. Es una profunda satisfacción contar con su presencia hoy aquí y finalizar este repaso por los 20 años de la Comisión Mujer y Ciencia con una cita de otra mujer premiada con el Nobel de Física, y no es Marie Curie, es Andrea Ghez, que nos recuerda que lo más importante que podemos hacer para impulsar a las mujeres y a las niñas hacia las ciencias es mostrarles que es posible, que es un camino que pueden tomar. Y añadimos de nuestra cosecha que puede y debe ser reconocido. Muchísimas gracias.
Muchísimas gracias, Teresa. Bueno, comprenderán que es muy difícil hacer una laudatio en un tiempo corto de una científica como la profesora Strickland. Lo voy a intentar lo mejor que pueda. Donna Strickland, desde 1997, es profesora del Departamento de Física y Astronomía de la Universidad de Waterloo, en Canadá, donde dirige el grupo de láseres ultrarrápidos. Ha trabajado, entre otros sitios, en la Universidad de Princeton y en el Laboratorio Nacional Lawrence Livermore y, como imaginarán, tiene numerosas distinciones y premios, del que destaca el Premio Nobel de Física de 2018, que se concedió por las invenciones revolucionarias en el campo de física de los láseres. Lo recibieron 3 investigadores, Askin por las pinzas ópticas y su aplicación a los sistemas biológicos, y Donna Strickland y Gerard Mougon por su método para generar pulsos de alta intensidad ultracortos. Este descubrimiento es de una gran importancia, ya que profundizó y amplió el conocimiento sobre la luz y su interacción con la materia, descubrió una técnica para amplificar la potencia de los pulsos y desarrolló esa técnica y la puso en funcionamiento. En resumen, comprendió y controló el proceso. Esto marcó el comienzo de un campo nuevo, permitiendo desarrollar aplicaciones inéditas para la utilización de los láseres que ayudaron a mejorar nuestras vidas. El descubrimiento lo realizó durante su tesis doctoral, bajo la dirección de Gerard Mougon, en la Universidad de Rochester, y se describió en su primera publicación científica en 1985. No era un campo fácil el de los láseres para destacar. Este campo tiene sus inicios en los años 50, basado en una idea de Einstein de 1916 sobre las líneas espectrales atómicas. El primer Nobel de este campo se concedió en 1964 por trabajos fundamentales en el campo de la electrónica cuántica que permitieron la construcción de osciladores y amplificadores basados en los principios de Maser y láser. En los años 60, en el 1960, se construyó el primer láser de rubí y luego se desarrolló durante esos años de una manera enorme, atrayendo a muchísimos científicos que, como verán, debían ser todos muy listos, porque ya en 1984 otros 3 científicos obtuvieron el Premio Nobel, justo cuando Donna, me imagino, que estaría buscando un láser de alta intensidad para poder estudiar los sistemas no lineales. Y se otorgó por el máster de hidrógeno y por la técnica de atrapar iones. En 1997, otros 3 científicos fueron premiados por el método de enfriamiento y confinamiento de átomos con láser. Y en 2005, Otros 3 científicos, ya van 12, premió la contribución a la teoría cuántica de la coherencia óptica y a la espectroscopía basada en láseres. Es decir, era un campo lleno de genios y era muy difícil meter ahí la cabeza. Sin embargo, Donna Strickland consiguió vencer el talón de Aquiles de los láseres, puesto que tenían la potencia de los pulsos limitada. Ellos consiguieron un método que les hacía de una gran potencia y abría una cantidad y un campo nuevo para el desarrollo no solo de la ciencia básica, sino de una gran tecnología. Pero este premio tiene además otra singularidad. Como ya se ha dicho, desde 1963, es decir, durante 55 años, la Fundación Nobel no encontraba ninguna mujer con contribuciones suficientes para un Premio Nobel de Física, aunque yo creo que la buscarían. Por eso, cuando en 2018 se consiguió este premio, se cumplieron los deseos de muchas mujeres y, sobre todo, se confirmaba una reivindicación que, como ha dicho Teresa, sí, nosotras podemos, que parecía que no se daban cuenta. Como dejó escrito Alfred Nobel en su testamento, estos premios se concederán a aquellos que hayan aportado el mayor beneficio a la humanidad, en concreto el de física, a la persona que haya hecho el descubrimiento o invención más importante en el campo de la física. La profesora Strickland cumple sobradamente estos requisitos. Paso ahora a leer el acta de resolución de la medalla de oro. La presidenta del Consejo Superior de Investigaciones Científicas, en uso de las atribuciones que tiene conferidas y previo informe favorable del Consejo Rector, resuelve conceder la medalla de oro del CSIC a la profesora Donna Strickland en reconocimiento a la extraordinaria relevancia científica de su investigación y la trascendencia de sus conocimientos, de sus descubrimientos en el campo de la óptica. Madrid, 30 de junio de 2020. Ruego a la señora ministra y a la señora presidenta del CSIC que suban para entregar la medalla y el diploma acreditativo. Profesora. Bueno, pues misión cumplida y ahora tenemos la inmensa suerte de que nos cuenten en primera persona y en tiempo real un descubrimiento que cambió un campo científico. Muy pocas veces se tiene esa oportunidad, incluso a los que estamos en este negocio, muy pocas veces podemos hacerlo. La profesora Strickland nos va a contar su descubrimiento. Muchas gracias.
I must speak here, right? Okay. First, let me thank everyone, CSIC and the CSIC Women in Science for honoring me with this gold medal. It's very special. It's always wonderful to have opportunities to talk about the importance of science and society. I am struck about the incredible work that the women in science have done here in Spain, because I'm sure we all noticed that nobody but women have spoken today, and that the president of CSIC is a woman, and that the Minister of Science is a woman. I find all quite amazing, so congratulations. So this is the official title of my talk, but I understand there's many young people in the room. So the unofficial title of my talk is Why Was I the Lucky Graduate Student that got to do Nobel Prize winning work? And it is because I was the first of Girard's students that was not interested in just trying to make the pulse shorter to measure something faster. I was the first one assigned to try to make the pulse shorter so the intensity could get higher. So that's really why I was the lucky student, and I'm going to explain that in my talk. The other thing that I hope everybody takes away, because I understand that not everybody in this room is a scientist, and it's already been mentioned today that this is one of the things I like to stress, is that it is important for science to continue to do fundamental or basic research and applied research, not necessarily by the same people, but that it's important for the field of science to keep moving forward. And so I'm going to walk us through 150 years of research, where it was scientists still trying to figure out how light and matter interacted that brought us the laser. And when the laser came along, it changed how intense the light was. That changed how light and matter could interact. And that got us into this new field of nonlinear optics. It was nonlinear optics that stopped us from making the laser intensity go higher. And so this is why Girard and I had to invent jerk pulse amplification. And when we got that invention, it again changed how light and matter interacted. And so that's what brought us to the machining of glass. And so each step of the way, we have to do fundamental science so that we can then apply it to the next technology. So I hope that those are the two main things you get from this talk. So let's go back 150 years. It would be true even before that. People still did not understand, after looking at it for a long time, was light a wave or was light particles? Nowadays, we're still questioning this, but now, today, we can have light be both a particle and a wave. But back in the 1800s, it had to be one or the other. And there was reason to think that it should be either one of those things. It was a theorist or a mathematician who showed us with this beautiful theory that we use to this day that light just had to be a wave. And it was such a strong theory that most scientists went along with it, and this is why we still use it today. Light had to be a wave. But as an experimentalist, I will tell you that a theorist can say something is true, but only an experimentalist can prove that it is true. So the experimentalists had to think, what would be the definitive experiment that would prove light was a wave? And they came up with an experiment that is analogous to if you've ever gotten the chance to walk on a beach, and a stony beach. We know that when the waves are small little ripples, they do not move the stones on the beach. But when the waves are high and come crashing in, the stones get pushed up the beach. And so that we all understand by watching this that the power in a wave is the height of the wave, not the distance between its crests. So the experimentalists set up this experiment. They used the different colors of light. I'm always going to just refer to the colors that we see with our eyes. So that you will see the longest distance between the crests, we call the wavelength, that we see is red. The light that we see the best is green, which is why now laser pointers are green, like this one. And then we see all the way to violet light. The distance here is not quite half, or this distance is not quite twice what violet is. So if you're a musician, you will know about an octave. An octave is a factor of 2 in the audio frequency or wavelength. The frequency is the opposite of wavelength. That's how rapidly the crests come at you. So we have these different colors of light. The scientists shone this light of different colors onto material, and they wanted to watch the electrons come off. And they expected that as they turned up the power, which means the height of the wave would get higher, then that electron would fly off at a higher speed, just like the stones on the beach. When they used red light, the longest wavelength light, no electrons came off. No matter how powerful they made it, no electrons came off. When they used green light, then electrons came off, but at slow speed. When they turned up the power, more electrons come off, but still at low speed. And finally, when they used violet light, then the electrons came off at high speed, and again, when they turned up the power, more electrons came off, but always at that same high speed. So this said that the energy had to do with the distance between the crests and not the height of the wave. And so this threw scientists back, wondering what was going on. This, again, is something that I like all people to understand, is that when scientists say they know something, they only know it for the moment, okay? So we thought we understood it. So when we did the experiment, though, then sometime after that, it was Max Planck who realized that we cannot turn the power of light down to zero continuously. There is a minimum energy unit that it gets turned down by. This minimum energy unit is what we now call the photon. He also noted that the energy of a single photon was indeed given by this frequency, the inverse of the wavelength, how rapidly the crests come. And so that the energy is indeed, for a single photon, given by its color. So we, again, just to get back to energies that we understand in our everyday life, the one that we get is gravity. We all get that if we want to, I'm going to show how Canadian I am. You probably here in hot Spain don't get to go sledding, but in Canada, one of the things we love to do is go sledding down hills, and we know if we want to sled fast, we must start at a higher hill to be faster at the bottom, okay? We also know that it takes more energy to walk a mountain than just a few steps. And so we understand height as energy, and so I'm going to use height here. So again, if you imagine lifting something very heavy, we would also know that it takes more energy to lift it higher up. So now, in understanding Max Planck's vision of a photon and an energy of a single photon, we will use height as an example. And so this red light, which has the longest wavelength, or the smallest frequency, is then the smallest photon. And so we're going to think of a red photon as a child-sized photon, and if they tried to pick up the electron, they can only pick it up this high. The green light then is higher and can pick the electron up higher, and the violet light can pick it up almost twice as high as the red photon. Now let's look at those experiments. This is what? Now Albert Einstein probably won the Nobel Prize for many things, but what it is stated in the citation he won it in particular for is explaining this effect that we call the photoelectric effect. And so he used Planck's idea of photon energy. And so you can understand the photoelectric effect by thinking about, now we're going to have the photons playing basketball. And how fast does the ball go through the basket? Now, they're going to be playing with a child-sized basketball net, and I'm sorry that I get that soccer is very big here, but so you have to go with this. It's a well-known sport in the United States, but I will tell you it was invented in Canada. So it's important to know. So now we're just going to have a child-sized net, but even with a child-sized net then, a child-sized photon cannot dunk the ball. When you turn up the power then of these red photons, you would only have many, many more child-sized photons all around the net, and none of them can dunk the ball. So this is why electrons did not come off with red light. Now when you use green light, and you have these adult-sized photons, and this is why I only play basketball with a child-sized net, you can now dunk the ball. But you see you're the same size, and so the ball is going slowly through the net. Again, if you turned up the power in this photon picture, you have many more photons at play, but they're all the same height. And finally, your violet photons then are like pro basketball players. So if you don't play basketball, it means you're very tall, okay? And so now you have these very tall photons, and when they drop the ball, it will be going fast through the net. And this is how we now understand why violet light sends off the electrons with high speed. Again, if you turn up the power, you would have more of these tall photons all around the net, and you would have more electrons come off, but the height is given by the color. So this explains the photoelectric effect. Usually in our classes when we're explaining the photoelectric effect, we are explaining the quantum mechanics of it, the fact that the light has this very given energy. But for this talk, I am starting with this. This is just one example of how light interacts with matter. It is the one that I will end my talk with, only at the high-intensity version of it. It's also, obviously, what Einstein won his Nobel Prize for, so I like to use it for that reason. But for this talk, it is an example of a linear interaction. And what I mean by a linear interaction is that it's always just one photon interacting with one atom at a time. And if that photon energy is bigger than what the atom is holding on to its electron, then the electron can go with the difference in energy, because energy is never created nor destroyed. And so this is how we understand it. It's one photon at a time with one atom at a time. This makes it linear, so that when you bring in more photons, they will interact with more atoms and send off more electrons. But the interaction is always one at a time. So if you double it, you will double the current. If you triple, you will triple it. And so that's why it's linear. So this is a linear interaction. And by 1905 then, scientists thought, we've got it all figured out. We understand light, and we understand how light interacts with material. And then along came this amazing woman, Maria Goeppert-Mayer. Now, she's famous for being the second woman to win a Nobel Prize in physics. But that's for work she did in the 1950s when she was working at Argonne National Lab. But when she was still a graduate student, working in Germany under Max Born, she was the one who asked the question, why can't atoms absorb the energy of two photons at the same time? Why are they stuck, always just playing with one photon at a time? She started a whole new field of physics. She could have maybe won a Nobel Prize for that, but she didn't. So, as a graduate student. So she explained that if she talked about two-photon absorption, but I'm going to stick with my photoelectric effect. And so now this is multi-photon ionization, where the electron will come off the atom. But now, if the basketball net is too high to have a red photon cause it, if it could absorb the energy of two photons at the same time, it would look like something taller than a violet photon, so it's really an ultraviolet photon, and the electron would come off with that great amount of energy. She showed us this should happen theoretically in 1930. She wrote the paper in 1931 and told us that atoms can indeed absorb the energy of two photons at the same time. Just nobody had seen it. And nobody saw it for another 30 years. It was Peter Franken's group at the University of Michigan that was the first to see it. They were the first to see a nonlinear optical interaction, so you'll see I've changed the name. If you do multiphoton physics, you are usually the atomic or molecular physicist watching what happens to the molecule or the atom. And if you're an optical physicist and watching what happens to the light, you are doing nonlinear optics. That's a very subtle distinction, but this one is going to be an optical experiment, because what happened is that they set up an experiment where the atoms indeed could absorb two red photons, but not have the atoms really absorb the light and hang on to it, not have it be ionized, but just momentarily hang on to that energy and then release the energy, not as two red photons, but as one photon with twice the energy. This is what we now call second harmonic generation. And so they got to see this in 1961. They saw it in 1 part to 1 million, 1 part to 10 million. So it was a small effect, but they saw it. And then that begs the question, why did it take 30 years? Maria Goeppert-Mayer told us it should happen, and we didn't see it for 30 years. And the reason we didn't see it for 30 years is that it wasn't until 1960 that the laser was invented. And so this is my Nobel talk, so I do pay homage to all the people that did win the Nobel Prizes in this field before me. And so Basov and Prokhorov were working together in Russia when Charles Townes was working independently in the United States, and they invented the maser. M stands for microwave, where L stands for light, and light is the part that we see with our eyes. Technically, it is easier to make lower energy photons have this process. This is why it started with the maser. Art Shallow then, a few years later, came along, and he's one of the people credited with figuring out how to change the technology so it would also work for light. But it's really this man who did not get to win a Nobel Prize. It was Ted Maiman working at Hughes Aircraft on May 16th, 1960, that showed everybody he was the first to figure out how to make it work with optical light and developed the very first laser. And so it was 1960 when it came along. So then, what is so special about the laser that would make an atom absorb 2 photons when they hadn't seen it before? Well, first, to understand regular light that we have here shining on us and shining on the screen, it works to light up this room because every color of light comes out. White light means this, if your eye sees white, it's seeing every single color that we can see. And so a regular light bulb will send light of all the colors. Also, it lights up the whole room because a light bulb will send photons in every single direction. And most importantly for this talk, each of these photons don't care what any of the other photons are doing. If one will go in this direction, at this color, at this time, and another one says, I don't care, I'm going in my direction, my color, and my time. Whereas with a laser, you can see that you see my little green beam there very brightly, even though it's only 1 milliwatt and hundreds of watts will be on that screen. You see it because all the light's in this one tiny spot. Coming from a laser, you'll have one color. This on the screen is red, but I'm using green here. It all goes in one direction, and that's why it becomes a tight point and not lights up the whole sky. But most importantly, all the photons know what each other are doing, so that when one is peaking, they're all peaking, and when one is troughing, then all are troughing. In this way, then, classically, in this idea of a wave, we add them all up, what we say coherently, to become a giant wave. And this is why the laser light is more intense, power per unit area. This is why this green beam shines so bright. So now I like to think about the nonlinear optics, so still in the photon picture, and so the classical picture. And so again, because they're all regular light has all these different colors, I like to say they're each dancing to their own beat, okay? Remember, frequency is how rapidly. So they're all dancing to their own beat. They also don't care how they're all dancing, and this is why they cannot crowd onto the dance floor. Now, we try to get them to crowd onto the dance floor by using a lens and squeezing them together to make the light down to a point. But we can only focus light to its wavelength. The wavelength of light is about 1 micron, a thousandth of a millimeter. Just so you know, your hair is on the order of 50 microns. So it's about 50 times smaller than this, which seems quite small, until you realize that the size of an atom is 10,000 times smaller than that. So if you look at the interaction volume of a single atom and ask how likely is it that there would be 2 photons in that volume at the same time with regular light, there's almost 0 probability that there would be 2 photons in that interaction volume at the same time. So you cannot absorb 2 photons at the same time if they're not there. But when the laser came along, and let me say that Nicholas Bloomberg won at the same time as Art Chawla, but he won again for laser spectroscopy, but he's considered to be the father of nonlinear optics, so I left him for this slide. But now that we have a laser, and they're all the same color, now they're all dancing to the same beat. And not only are they all dancing the same beat, but they care how each other are dancing so they can all dance together. And this is why they can squeeze onto that dance floor. So that finally in 1961, using a laser and a lens to squeeze it together, they were able to see 2 photons in that interaction volume at the same time. And so they could see the absorption of that energy of 2 photons at the same time. So the laser brought us to this field of nonlinear optics. So now finally, what has any of this got to do with me? So when I joined Gerard Maroux's group, he gave me a paper written by this man, Stephen Harris, who was a professor at Stanford University. And Stephen Harris was asking the question, can we get atoms to absorb more than 2 photons at the same time? It would be great to have this coherent radiation where all the photons talk with each other, not just visibly where we can see, and more of the lasers were actually in the near infrared where we can't see, but lower energy, easier to do. Could we not get this light up well past the violet to the ultraviolet and maybe even to the extreme ultraviolet and possibly even X-rays? We are still trying to to do that to this day. And so he came up with a theoretical way of possibly doing it. And Gerard gave me the paper and said, see if this is something you'd be interested in. If so, figure out how to do it with one of our lasers. So I came up with a scheme that would absorb 9 photons at the same time to make one extreme ultraviolet photon. So my PhD project then had 2 parts. The first part was to figure out how to make the medium, which was going to be twice ionized nickel, and it had to be kept cold. I never figured that part out, so we won't talk about that half of my thesis anymore. The other half of my thesis was I didn't want to cram 2 photons into that small volume. I wanted to cram 9 photons into that small volume. So I didn't need just a laser. I needed a really intense laser. That part obviously worked, which is why I'm here talking to you today. And so that's the part we'll discuss. All right, so how does one make a laser intense? So I have this laser beam that I can make here with this little gizmo. And I can actually make a 1-second light pulse just by opening and shutting my finger, okay? Now let's say, we sort of have windows, but they're kind of cloudy, so I can't do it, and I wouldn't, just in case milliwatt is too much for somebody's eyes. But if these were real, clear windows, and let's say the moon is out that direction, and I sent my 1-second light pulse towards the moon, okay? It amazingly to me, even after working with lasers for 40 years, would be 3/4 of the way to the moon before I shut my finger. It's amazing how fast light travels, right? It took me 7 hours to fly here from Canada, but in 1 second, light can get almost to the moon. So that's how fast light travels. If you say you have a 1-second light pulse, that 1-second light pulse, if it was not impeded by something, would last or be strung out over 300,000 kilometers. Now that first experiment done in nonlinear optics with just 2 photons, the very first lasers were 1 millisecond or 1,000 times smaller than that. So that's still 300 kilometers. It's still a pretty long line of light. I will also say that they didn't use 1 millijoule like I discuss here, but used 1 joule. So why am I showing an energy of 1 millijoule? I've already said the light from here is not hundreds of watts like the light bulb, but 1 milliwatt, 1,000th of a watt. All right? That means every second coming out of here is 1 millijoule of energy. I can shine this light on my hand, and if I hold it really, really still, which I have trouble doing, I can almost feel my hand warming up in that spot. So it looks like, well, what's the big deal then? A millijoule of energy can't be very much. But I'll tell you, it only takes a millijoule to cut the cornea of your eye, and it only takes a millijoule to cut the glass in your cell phones. And so what's the difference between the millijoule coming from here and the millijoule that can cut glass? We did not leave the pulse being 300 kilometers long. My project was about taking a millijoule pulse and making sure it got all the way down to a picosecond, which is a millionth of a second, or 1/3 of a millimeter. So all the energy that comes out of this laser and stretches out over 300,000 kilometers is squeezed down so that it's now all squished into just 1/3 of a millimeter, all right? And this is how we got the photon density up so high. So how did we actually do it? Let me go away from the moon and come back to Earth. And we're going to go to the University of Rochester, where I did my PhD, and I did my research at the Laboratory for Laser Energetics. This is a Department of Energy funded facility for laser fusion. Okay? So this is where I did my work. This was the very first laser in Gerard's group that I got to go see, and I actually was shown this laser by a fellow Canadian student who took me to introduce me to Gerard Moreau that first week and show me this beautiful laser. And I just saw this red and green laser and thought, how fun would that be to work with this laser? It would be like being around a Christmas tree all year long. I never got to really work with this laser, but that's a different story. Anyway, this is an example, a dye laser. And so this is actual liquid dye coming through here, being pumped by this green laser and becoming this red. Okay, so it is called a dye because if this orange gets on your clothes, it will dye your clothes orange. Okay, so this is an example of a very short pulse laser. Gerard already had short pulse lasers in his group. This laser is actually 10 times shorter than what I'm talking about, so only 1/30th of a millimeter. So very short pulses, but a dye laser cannot be made energetic. Across the lobby of LLE was the laser that was the whole point of the Laboratory for Laser Energetics, because it was studying laser fusion. And laser fusion is an application that requires energy in to get energy out. And so this is the laser as it appeared back in the 1980s. So just to give you a scale, and since I understand you like soccer, or maybe you call it football, or you probably call it something in Spanish, so it doesn't matter. This is a football-sized field, okay? And this thing here is the size of a human adult. So this is a large, large laser. And to get energy out, you need a large laser. I'll explain that later. So we had very energetic lasers. This could now do a kilojoule of energy. That's 1,000,000 times more energy than what I'm talking about, okay? So we had big energy lasers, and we had short pulse lasers, but we could not put them together. That's why we needed to develop short pulse amplification. So this is now my first Nobel picture slide that's in color, because when I prepared this talk, it was present day, and all the rest were history. Of course, we're now history. I should turn it to black and white, but I won't. So this is Gerard and I partying on December 10th, 2018 for our Nobel Prize. So this is what we did to win a Nobel Prize, and the beauty of it is in its simplicity. So we want what I call a laser hammer. I want a lot of energy in a short amount of time. Why do I call it a laser hammer? Because if you imagine pushing a nail into a piece of wood, it won't go. But if you pick up a hammer, in it goes. Sometimes the experiments like fusion require energy, but sometimes experiments, and nonlinear optics is one of those types of experiments, require the energy density, or the time to be short, squeezing all that energy down. So we want a lot of energy. We want it in a short amount of time. The problem was that when they used to try to amplify short pulses directly into an amplifier, the hammer was inside the amplifier, and we drilled holes in the laser rods. This stopped people from doing it in the 1970s. It sent some people off to go, I wonder why that's happening. And so the nonlinear optics people had to go, I wonder why that's happening. But the laser jocks like me were told, don't put short pulses down our very expensive lasers. They just don't do it, okay? So we want the laser hammer. We don't want it in the amplifier. So this is the whole idea. We start with our low energy short pulses from the laser itself, and then we go ahead and stretch it and make it a long pulse of light so the density of photons goes down. We can then safely amplify it up to the maximum energy that the amplifier will give. And then after it's safely out, we compress it to a short pulse. Now we could have called it stretched pulse amplification, because for everybody else that would explain it, I guess, better. But we thought chirped pulse sounded nicer. And a bird's chirp is the fact that its audio frequency changes in time through their pulse. And so this is now our frequency changing in time through the pulse, and that's why we call it chirped pulse amplification. So how did we do it? So now this looks like the very same laser I showed you before, because it is. But now it's got a new title, and that's because we're not watching this part of the laser anymore. It's this laser back here is going to be the laser I start with. This laser makes light in the infrared, where you can't see. So you don't see the beam coming this way, but there's a beam, and it's a strong beam, 2 watts coming. So 1,000 times more than this guy coming this way. This is a frequency doubler. The same thing that the Franken group did in Michigan, but only had 1 part in a million to 10 million. Now, because this is short pulse, the intensity is high enough that it goes double. This is why green is twice the energy of the infrared, and we now have a good strong green beam, but it's still only 10%. Our laser mirrors are so good that 99.99% of that light is turning the corner, but the infrared is coming right on through. And so that was the infrared beam that I was given to do my experiment. And there I am as a young student getting ready to do this experiment. This is for the picture was taken for the quarterly review. They always put students on the cover of the quarterly review of LLE, I assume to show how they were educating the youth. And so it was my turn. I am wearing the lovely kind of laser goggles that we had back then. But I will also tell you that the photographer, and I've been photographed a lot here today, the photograph there did not like the green glass in front of my eyes, and so I'm really just wearing frames. But it's okay, because you couldn't tell if my infrared laser was on or off, so it was off. I'm still safe. This is where the beam dump used to be. This is now the way I get light into my fiber, and it is this fiber that is going to stretch the pulses for me, and then it comes out here. And so you'll also see there's no room left for me in this lab, and so actually once we got the light in the fiber, this is why I know it's the beginning of the experiment, because the light's still here, this fiber was strung through the air ducts to the other end of LLE into a lab that had been cleared for me to do the rest of the experiment. So then I'll just explain how this works. First, you have to understand that in order to have a short pulse, even though I keep talking about how lasers only have one color, you cannot have just one color and have a short pulse. We need many, many, many colors to have a short pulse. Now, if you just allow all the colors to laze at the same time, you're back to a light bulb. So we have something in our laser called a mode locker. It performs the same thing as a symphony orchestra conductor. Now, when you go to hear an orchestra play and you listen to them warming up before they start to play, they sound terrible. They sound terrible because they're all playing their own notes, listening to themselves and not caring what the other people are playing. That's the same as light from a light bulb. It's just noise. But when the conductor brings down his baton and says, play now, and all of the notes play together, you get beautiful music. And so this is what our mode locker does. It says to all of these colors, see we have all the red to the violet colors, at this point in space, go now. But when you go away from the space, because each of the colors have different distances, so you'll see the violet comes up very quickly and the red is very far apart, that you don't have to go very far away until you have as many peaks as you have troughs. The black line is the addition of all these colors. The more colors you bring in, the shorter the pulse will be. The faster that goes to zero. And so we have these types of lasers that have all these colors to make our short pulses. Now when we go in the fiber, once we go into a medium, different colors of light travel at different speeds. So now the red light is just going to run through the glass. The green will walk through the glass, but the violet light or blue light sort of crawls. And so at the end of my fiber, oops, keep running. There we go. It's now the red is out ahead of the blue because the red travels faster than the blue. And this is how we make our chirped pulse, and this is how we stretch our pulse to be long. Once we have the long pulse, now we're going to amplify it. I do like to point out, I don't know how many physicists are here, but I am not an atomic or molecular physicist. I am an optical physicist, and so only photons have personality in my talk, and so these are atoms, okay? So the atoms sit there and they need to get excited, so we'll have some way to excite them. In the case of my laser, it was xenon flash lamps, so regular lights, but they put out ultraviolet. If you design your amplifier well, most of the light now will be in an excited state. Certain types of lasers, like the dye laser, will not hang on to that energy. They'll just let their energy go. This is why they cannot be made big and turn into big energy lasers. But the glass laser that I used is one of the ones that will store this energy. So in one case, it's like they will run a dash. This type of laser is a marathoner. It goes, I can hang on to this energy for a long, long time. And so it sits there waiting for a photon to come along. And there's the happy photon. And now you'll see that the photon and the atom have actually the very same energy. And so this was the thing that Einstein showed us in 1916, that instead of absorbing the light up, it can also cause the atom to fall back down. That's what we call stimulated emission. This photon says to the atom, I'll take your energy, and we'll walk together hand in hand as two photons. The two photons will meet two more atoms, become 4 photons, the 4 will become 8, and so on. All lasers start this way with one noise photon going in the right direction. But you can see that most of the energy gets left behind here, so it's not efficient. This is one of the reasons we have mirrors to send the beam back and forth and back and forth. We must get to that place where we now have so much energy. Again, I'm going to use a Canadian analogy. It's like a snowplow, and it's going to plow through and take all of the energy out of the atoms. And so this is why the lasers have to get very big. We start by focusing tight, because we start with just one photon, and we get up to that energy per unit area. For glass, this is 5 for the physicist, 5 joules per square centimeter, one of the largest. But then if you want more energy, you make the beam a bit bigger, you go through an amplifier until you get that same level of energy per unit area. Then you make the beam bigger and do it again, and then you make the beam bigger. And this is why for the kilojoule laser, and now we have megajoule lasers, that the lasers have to get to be so large. Because eventually to get the whole kilojoule, you have to have a big area. So for each laser, we know what the number of photons per area should be. But if we don't want a hammer, that tells us the limit of how many photons per volume you can do. So we knew that we needed to stretch our pulse to make it 1 nanosecond, a billionth of a second long. This also works better in the United States because a nanosecond works with American units. It's exactly a foot long. Okay, so this long a light. So that's how we know how far we have to stretch it. This thing is getting in my way. So now we just need to compress it. We use 2 things called gratings, and we make them parallel. This is the same. We've all seen light go through prisms and make the colors bend at different angles. The gratings do it even stronger. And so if you watch, the red is out ahead of the green, ahead of the blue, but the red bends more than the blue. So when they come off, and they'll come off the second parallel grating all parallel with each other, but they've all caught up to each other, and that's how we make our pulse short, and that's the whole thing. So that was the result. I still remember that it was a Thursday night in 1985 when I got this to work, and that my friend and colleague Steve Williamson was with me because he had the new tool that could actually measure that the amplified pulses were short. Without that, I would not have been able to measure it, and he came in and helped me measure that indeed it was short, and this is just a way of measuring it. Okay, so now back to my thesis. I never did figure out how to do the harmonic generation. So I luckily had a scientist from University Laval in Quebec want to be the first person to do science with the new CPA laser, and he came down and helped convince Gerard to just let me do multiphoton ionization. So now it's back to the photoelectric effect, but now we have a very intense laser. And so if it was going to be this nonlinear thing, in order to get the electron kicked out of this well, again, we're talking about height, we have to get this electron up here so it can leave. It was going to take 11 photons. I don't know how many are drawn there, not as many as 11. It would have gone to the 11th order in power. It did not. So it was not nonlinear optics anymore. We now had the light so intense, we didn't have to think about the photon picture anymore. We were back to the light just being a giant classical wave. And this giant wave just simply tipped it over, and the electron was free to leave. And so it changed again how light and matter interact. And from that understanding, other scientists figured out how to cut glass with such a laser. I'm just going to quickly go through this now. This is sort of the intensity as a function of year. We started with the laser in 1960. This makes shorter pulses. We came along in 1985. When Gerard first started showing these curves, we'd be up here by now. You'll see that we are rolling over. So I do like to point out to all young people, it's time for a new Nobel Prize winning idea to kick us on up again, okay? We want to get up here. This is where we would break the vacuum. So I'm just going to say that, the vacuum is maybe nothing. A lot of people think vacuum means there's nothing there, but our high energy physics friends tell us, no, it's matter attached to antimatter. We're hoping that we have so much intensity that we're going to come in. I use my hands too much. We could focus the light down and actually blow apart the matter from the antimatter and maybe change the vacuum. We're still hoping to do it. I hope to see it in my lifetime. So somebody come up with that new idea. I will also point out that this started in the United States, but somehow Europe has eaten our lunch. This is at the Eli facility here in Europe, and Korea has the world's most intense laser at 10 to the 23 watts per square centimeter, where I was down here at 10 to the 13. That's what I did that got me sitting beside the King of Sweden, and thank you very much.
Muchísimas gracias, profesora Strickland. Tiene la palabra la ministra de Ciencia e Innovación.
Bueno, la verdad es que es un placer, es un honor estar hoy ya en este acto tan importante. Profesora Strickland, muchísimas gracias. Gracias por haber aceptado este premio, que es el premio más importante que tiene el Consejo Superior de Investigaciones Científicas, el máximo reconocimiento y que solo lo tienen 3 mujeres. Así que también rompemos otro techo de cristal propio del Consejo Superior de Investigaciones Científicas. Gracias también por explicarnos de manera tan sencilla cómo funciona la ciencia, con esa generosidad. Yo he vuelto por un momento a las aulas de la universidad. El darnos a entender que, por supuesto, la ciencia, todo lo que nos ha contado de manera tan escueta, es tan compleja, que los científicos os cogéis de la mano unos a otros, de siglo en siglo, a hombros de gigantes, como decía Eloísa del Pino. Y este mensaje es sobre todo para todos los estudiantes que nos acompañáis hoy. Que sepáis que es abrumador, por supuesto, escuchar una Premio Nobel, pero también ha sido muy generosa, descubriéndonos a la persona, una mujer simpática, una mujer cercana, próxima, que estoy segura que cuando era de vuestra edad no soñaba ni imaginaba nunca que iba a ser una Premio Nobel, pero en definitiva no le ha faltado nunca el hambre de seguir contestando y dando respuestas al mundo. Eso es la ciencia, eso es la profesora Strickland. Gracias por todo tu trabajo y os aconsejo que tengáis hambre, siempre, hambre de dar respuestas y que no esperéis que las respuestas os vengan dadas, sino que vosotros podéis ser perfectamente y vosotras las próximas Premio Nobel y los próximos descubridores de las respuestas de la vida. Y ahora nos tenemos que ir, tanto Donna como yo, que tenemos una recepción por parte del presidente del Gobierno. Así que gracias y felicidades a la presidenta del CSIC también por todo el trabajo que hacéis en pro de la ciencia y en pro de las mujeres. Gracias.
Bueno, muchas gracias a todos por su presencia. Ahora lo podemos celebrar con un refrigerio.